Come on in, everyone. Feel free to ask me any questions while we're waiting. Looks like we got a lot more than 8 people, but we only have 7 people in here, so figured. Again, feel free to ask me any questions if you have any while we're waiting. We got about 2 minutes before class starts. We're starting chapter 4 today. Evelyn, I like your profile pic. Cool Milky Way picture. I just ate, so I'm pretty confident there's a big hunk of broccoli or lettuce or something on the tooth. So if I look like I'm missing a tooth, that's what happened. Your homework won't come up. It's giving you an error. Uh, Try emptying your cache and then open it back up. Sometimes that happens with all the homework systems. So if you go into your settings for your browser and do clear cache and then go back, open it back up, that might help you.
Yeah, could you extend it or whatever? Because I was trying to do it yesterday and it still wasn't coming up. It was giving me an error.
Yeah, make sure that works. But yeah, I can do that for you. No biggie. See if I'm even in the right place.
All right, thank
No problem. If you don't see me change it, just remind me or actually by text message would be best.
you. Yeah,
Oh,
I actually emailed you, but it was Sunday, so I wasn't expecting the answer.
oh yeah. Yeah, sometimes I clock out on Friday afternoon and don't mess with it until Monday or even Monday afternoon. So I've got a few more I've got to answer myself. But yeah, that kind of stuff, feel free to text me. That's not no problem. And I'll let me know if that doesn't work as well. But like I said, yeah, I can give you a 2 day extension or something like that. Anybody else have anything before I get started? It's time to get the class go rolling, so I don't want to waste too much time. No homework questions. We do have a test. I believe you guys told me you have your labs on Monday, not Wednesday. Is that correct? I think you had lab today.
Yeah, ours is at 7 later.
Oh, it's afterwards. Okay, gotcha. So what that means is you'll have lab tonight, but next week at this time after class, you'll actually have a test, and that test will cover chapters 1 through 4. So you already have an online test that I think part of it might even be due either tonight or tomorrow night. So make sure you get that done. That's actually excellent practice for preparing you for test 3, which would be what we're doing Monday online. I mean, face to face. So keep doing that. I may have enough time to make you a special test for test 3. I'm not sure yet, but just know that you should be covering chapters 1 through 4 on the test that happens in your lab, the face-to-face test. As I said, we are starting into chapter 4, and chapter 4 is called Dynamics, Newton's Laws of Motions. And the learning objectives are to calculate the net force on an object as a vector sum of all forces acting on it. So we've learned, for instance, how to add vectors and how to subtract vectors and how to multiply vectors by scalars and stuff of that sort. Now, what it turns out is when you have a force acting on an object and you have another force acting on the same object, it turns out the total force on that one object is the sum of the two vector forces. So you got to be able to add vectors to do that. 4.2, use Newton's second law to relate the net force acting on an object to its mass and acceleration. Objective 3 is to relate the weight of an object to its mass. Objective 4 is use Newton's third law to determine the force that one object exerts on another. And learning objective 5 is draw a free body diagram representing the forces acting on an object. So that's just some of the key stuff we're supposed to cover. I will tell you that basically Newton once said, if I have seen further than others, only because I stood on the shoulders of giants, which sounds like a really, really modest thing for such an arrogant man to say. If you know anything of the history of Newton, he was largely considered quite arrogant, a little bit of a curmudgeon, that sort of thing. But anyways, he was a very interesting character. Let's put it that way. So when he actually said, "If I have seen further than others, only because I was because I stood on the shoulders of giants," so it is kind of nice, and he certainly means it, because Newton's first law of motion is really just Galileo's law of inertia. When I look at Newton's third law, I remember seeing in a notebook of Leonardo da Vinci that something along the lines of, it is obvious that if an eagle pushes down on the wind with a force of 50 pounds, then the wind pushes back up on the eagle with a force of 50 pounds. That's definitely Newton's third law of motion. So there are some geniuses that he's gotten information from, but the Newton second law part is the part that he made up himself. And also that statement was made in front of the Royal Society, the head of which at that time was a guy by the name of Robert Hooke, who was one of his mortal enemies. And he was a bit of a curmudgeon as well. And he had a bit of a short man complex. So history tells us, I think he might have been like 4'9", 4'10", or something like that. So when he's saying, "If I have seen further than others, only because I stood on the shoulders of giants," he really means not hobbits like you, Mr. Hooke. So that's a little bit of the backside of it. There's all sorts of interesting stuff. There's a good little biography of Newton. It's only about this thick, and it's just called Newton, and it's written by Glib. I think it's Glib. I'm trying to remember his last name. But anyways, it's the same guy that wrote the book Chaos. And anyways, it's a nice little biography of Newton. It tells about his history. He did not have that pleasant of a home life, but he was fortunate that he had an uncle that could send him to Cambridge, but he also had a mom that could pimp him out and leave him without any ability to live life nicely, because she shook his uncle down for more money. So rather than Newton being able to go to school and maybe not have to do a lot of the nasty things he did, he had to do some of those nasty things because Mama said, "Well, I'm not letting him go unless you pay me too." So it was really kind of a sad thing. But he ended up cleaning out the chamber pots for the wealthy kids, which you can imagine is just a easy way to make friends at a university like Cambridge. So that was his life. But he did go on and do brilliant things. He believed that mercury was an elixir of life. He thought it would give him a really long life, and he literally took mercury every day of his adult life. And he did live to be like 80 something. That's not that abnormal, though. I'll tell you that, for instance, Lewis and Clark, Meriwether Lewis and William Clark, who basically searched the Western U.S. after our purchase of Louisiana from Napoleon, we've been able to track down exactly the paths that he's taken. They took specifically due to stool specimens that we found out west with mercury in it. So mercury is something that used to be taken as an emetic for an upset stomach. It can make you throw up or go the other side or whatever. So we have found that, and that should make you feel a little better. I know I used to freak out. I'm a little bit of a hypochondriac, so just the thought of eating some food with mercury in it would always creep me out. But now I find that these people have been eating quite a bit of mercury and we're just fine. So that makes me feel a little better. Still, I would not go against FDA guidelines. I'd just say if you end up, accidentally going over the FDA guideline once, it's probably not a big deal. So. All right, so that's Newton. I'd like to tell you more about him, but I really need to get started. So Newton basically wrote physics out in such a way that science had never been written before. We had Aristotle, who was a great scientist. We obviously had Kepler and Galileo and all these people. But really, to be honest with you, and this isn't Aristotle's fault, but Aristotle and his work kept science at bay for a millennia. I mean, it's really that bad. A millennium, excuse me. So, and actually might have been closer to two. But anyways, he had been a very complete scholar in that he sort of covered everything. He had a system that he had made up, and it was based on certain premises that were obvious to him and everybody that lived during his time, but aren't so obvious to us now. So, for instance, he had as a fundamental premise that there were 5 elements: the earth, wind, fire, water, and the 5th element would be the quintessence. I always make the joke that that's Mila Jovovich. She played in the 5th element with Bruce Willis. Poor Bruce, I feel bad for him right now, but he's probably the one that doesn't know too terribly much about it. But anyways, Mila played in this movie, and she was supposed to be, heaven. That's what quintessence is. It's the heavens, or the 5th element. And one of the premises of his logic was that the heavens are perfect and therefore they're immutable and unchangeable. So that means that anything that's going on in the heavens will have always been going on and will never stop and will never restart. Things won't speed up or slow down, because if they sped up, they're speeding up to from a perfect speed to an imperfect speed, or if they speed up, they were speeding up from an imperfect speed to a perfect speed, both of which are unreasonable, because the heavens are perfect at all times, not just after these motions. So that was one of the scenarios that they would abide by. And for instance, it was obvious to them that the perfect shape was the sphere. So everything in the heavens had to be spherical. So they actually imagined the earth being the center of a sphere, or a center of several spheres, and the spheres around it were a sphere that contained the moon, and then outside of that was a sphere that contained Mercury, and then Venus, and then the sun, and then Mars and Jupiter, Saturn. That was pretty much it. But these were seen as sort of crystalline spheres. So if you can imagine spheres made out of opaque material, and in some of the history, the idea was that there were actually little holes in those crystalline spheres, and outside of that crystalline sphere, or that nested set of crystalline spheres, was an actual fire. And what you were seeing when you saw stars twinkle was little holes in the celestial sphere where the light from the outside fire would shine through. And actually, if you watch the night sky over a long enough period of time, you'll see why they thought that. It looks quite obvious that there's this point directly above the North Pole of the Earth almost, that sits perfectly still, or very close to perfectly still. If you actually take a time-lapse photo, you can see it moves like this, but it pretty much is sitting still. So if you didn't have access to a photo like that, you wouldn't necessarily know that it's moving. So not only that, everything seems to be moving in such a way that, like, they had painted on the inside of the sphere, they had painted or punched holes in very specific shapes to make the shape of Leo and the shape of Gemini and all this stuff. And those shapes don't move towards each other, or don't, conform to different shapes over time. And they always, for instance, where we're at, they'll rise in the eastern half of the sky. They'll go up and to the right, up and to the right, up and to the right. They'll reach their highest point due south of us, and then they'll start to go down and to the right, down and to the right, down and to the right, and they'll set in the western sky. And if you look towards the northern sky, you'll see that things are going around in a counterclockwise fashion around the that one star that seems to be not moving at all. And that one star is called Polaris, or the North Star. And it is very close to being directly over our North Pole of our Earth. So if you just look at the universe, it does sort of look that way. And you can see why things like the crystalline sphere or the celestial sphere, as we use it, still comes in handy. In fact, we use that to teach astronomy so that people can understand the way the stars move and the planets move and stuff like that. So Aristotle had come up with this system, and actually it wasn't just Aristotle. There's a lot of people before him and after him, Anaximander, the Pythagoreans, and various other people from ancient Greece. There were other cultures other than Greece. We're sort of a Eurocentric group here in America. We're just now starting to learn more about world history as opposed to just European history. But what we know of is the civilizations that we found that we hadn't studied in the past. We're very much doing the same thing. So you can find in South America civilizations that were very much beholden to the stars and making predictions with stars, not unlike the ancient Greeks did, not unlike the ancient Egyptians did. So all of them seem to have figured out that something was important about the night sky. And in fact, the thing about the night sky is, or the night and day sky is really a big clock and a big calendar. You can learn how to read the stars at night, knowing what time of year it is, and you can use that to figure out what time of night it is. And if you know what constellations are up, you can use that to figure out what time of year it is and all that stuff. But Aristotle had done a lot of this. He'd made some sense of it. He even knew that the Earth was spherical. He had made an approximation for this Earth's circumference. And in fact, that approximation was way too small. It was about 40% smaller than it really was. And oddly enough, that happened to be the figure that Christopher Columbus had when he actually went to see about going to look for a passage to India. And had he had the real, more correct figure, they might not have approved it. He might not have even tried to sail it because the Earth would have been too large if it wasn't for this new continent. It might not have been large. It might have been too large for them to make a sea voyage all the way around with enough stuff to survive the mission. So there's a lot of neat quirks of history. The rest of the Aristotelian logic, though, in addition to the heavens being perfect, is that everything behaved as its matter was. So, for instance, the five elements, as I said, the fifth was the quintessence, but the first four is earth, wind, fire, and water. And the way that worked out is basically there was two types of motion. There was violent motion, and violent motion had to be sustained with a force. And then there was natural motion, and natural motion just happened because of the substance the thing was made of had a natural place. For instance, if something's made of earth, for instance, a tree, grass, a mud clog, or whatever, those things were made of earth, and their natural place was the center of the earth. Therefore, they tended to fall downward, and that was called natural motion. Whereas if you took that mud clog and you rolled it up into a ball and tried to roll it on across the ground, even a very smooth part of ground, that would be violent motion. And in fact, the only way it would keep going is by sort of its oomph that it already had for having motion, i.e. its inertia, or because of forces that have to keep it there. So that was the way Aristotle saw motion. He also saw that, motion, for instance, when you released a bit of earth, it would fall towards the center of the earth. And if you did the same thing with another piece of earth that was twice as heavy, then that thing that was twice as heavy would fall twice as fast. And if it was 3 times as heavy, it'd fall 3 times as fast. And if you burnt, for instance, a log, which was part of a tree, and you can see the tree literally growing out of ground, you'd see that now this tree is burning. It's partly earth. It now has gaps in it from where the fire has been burning through. So it's partly air. It's got fire on it. So it's partly fire, whose natural place is above the atmosphere. So now you've got an understanding of how the smoke rises. The smoke is rising. It's not rising very fast, though, because part of it's earth, and that's wanting to go towards the center of the earth. Part of it is air, and that wants to be above the air, the Earth's surface, and stuff like that. So they had, these really well thought out explanations for all the motion, including like how does an arrow continue to fly? Well, his picture was the tip of the arrow was ahead, and that split the air apart. And nature abhors a vacuum, and because of that, the air would squish down behind the arrow and give it a little push ahead. Guess what? Turns out that that's not really far off from what the hydrodynamics of an arrow flying through the air is. There is some, obviously, it's not a whole vacuum, but there is a decrease in pressure, and that does help the thing along. So some of that stuff is not too horrible. But in addition to Aristotle being the big brain in the room and everybody respecting him, in the intervening period, the world underwent a huge change from a bunch of different, I'd say, a bunch of different types of religion to the major religions of that time, which was Constantine introducing Christianity, and then the churches taking over and stuff like that. So what you get when you get to the time of Galileo and later even Newton is now a church that's largely in control of everything, that's had Martin Luther, who put his edicts on the wall and really caused quite an uproar. Giordano Bruno, who's been burned at the stake, later Joan of Arc as well. A lot of different things are going on. But in light of all of that, the Bible has been translated with respect to the understandings of Aristotle. So now if you start bucking Aristotle, you're not just bucking Aristotle, you're calling into question the very interpretations of Scripture. So it became a real problematic thing. Galileo was not one to worry too much about that, nor was sort of Newton, even though Newton was a much more quote unquote pious person. He bragged at the ripe old age of 80 that he was still a virgin. So he had never taken a wife. He only worked, really, is all he did. And he was quite the neat little specimen. For instance, he stared at the sun for such a long period of time that one time he had to go like 3 months without going outside at all because he had such bad migraines from staring at the sun. Or he was trying to figure out one time what the shape of the eyeball had to do with the visions you see. So he pulled his eyelid out and jabbed it with a knitting needle and pried it and then drew what he saw. And it was some pretty amazing stuff. So this is a very, very different kind of culture and different kind of ideas. And everybody was, measuring all they ate and drank and all they expelled and trying to see if mass was conserved and crazy stuff like that. But come to find out, Galileo went before the Spanish Inquisition, where he was probably showed the instruments they would use to cut his entrails out of his gonads and to lie them on his stomach and stuff of that sort. So he decided to recant. And luckily, the Pope at the time was his friend, who was previously a cardinal and had given him permission to write the book. So he ended up getting in-house arrest as opposed to some of the horrible things like Giordano Bruno had. But by doing that, he was sentenced to no longer teach anything about astronomy, anything about the heliocentric model of the universe, and that sort of stuff. So he went to studying motion. And while he studied motion, he came up with ideas of velocity and constant velocity and acceleration and constant acceleration. If you actually watch an object fall, it falls and it happens so quick you can't tell. Did that object fall and initially go 0 miles per hour and then slowly speed up? Or was it like it just jumped out of your hand with 3 miles per hour speed or what? It was really hard to tell. And Galileo knew that was a problem, but he wanted to understand motion because he'd already seen, for instance, in all the models of the universe, Jupiter was moving. So in the Tycho Brahe model, in the Kepler model, in the Copernicus model, all of those models had Jupiter moving, and what Galileo had seen was what he called the Medicean moons. We now call them the Galilean moons, Io, Europa, Ganymede, and Callisto, which were moons of Jupiter. Only 4 of the excess of 100 that are out there now. But anyways, he saw these 4, and they just constantly went around the planet Jupiter, no matter where Jupiter was. So he really needed to understand motion because at the time, the idea was if the Earth was actually moving, if the Earth was orbiting, for instance, the sun, then a bird sitting in a tree limb looking down, seeing a worm, if the bird was to lift off the tree limb to fly down and eat the worm, the planet would leave him behind. Yet here we are, where everybody agrees Jupiter's moving, and there's 4 moons that they see not being left behind. So he wanted to understand motion. So he first had to deal with the problem of how fast motion was, and he knew enough about what we would call trigonometry to realize that a ratio of vertical to diagonal can be related using what we now call trig. So yes, he could study vertical motion by studying motion at an angle, and then he could get back the information about the vertical motion just by using techniques of trigonometry. So he studied that. He studied things rolling down inclines, and he would roll a ball down an incline, and he'd make a note that it seemed to speed up, which gave him the impetus to come up with the idea of speed and velocity and that sort of thing. And what he even defined was that velocity or speed, a constant velocity or constant speed, is basically the kind of motion that always covers the same distance in a given unit of time. So if you choose the unit of time to be 1/10 of a second, and one time you measure it and over 1/10 of a second it goes 3 meters, and then you do it again, you'll find that 1/10 of a second it's going to go 3 meters there, and another 1/10 of a second it's going to go 3 meters there. Any 1/10 of a second interval is going to require it to go 3 meters. That's the definition of constant velocity. And if we add the velocity, and you have to add the vectors, which, like I said, vectors didn't exist in the time of Galileo and Newton. But that just allows us to also realize that it's not just the speed, how fast it was going, but also the direction mattered. He also reached the conclusion that there's something called acceleration, which is really how much your velocity changes in a given unit of time. And he decided to create constant acceleration, or define constant acceleration as that acceleration that changes the speed by the exact same amount every unit of time. So again, if we take 1/10 of a second, if the object went from 1 meter per second to 3 meters per second, then the acceleration was 2 meters per second per 1/10 of a second. And if you looked at any other time interval that was 1/10 of a second long, you should find that the velocity changes by 2 meters per second in each of those 2/10 of a second. And that would be the definition of constant velocity, or constant acceleration. And that's where he ultimately was able to show that when he rolled objects down inclines, they sped up. When he rolled them up inclines, they slowed down. So he hypothesized or reasoned that if they were going perfectly horizontal, they would neither slow down nor speed up. And that was a pretty big deal. And it's going to an imagination place where you can imagine more happening than you can actually do. He can't really make a perfectly infinitely long level surface. So he had to imagine what would happen. And he wanted to make sure that he was further right. So he would actually allow things to roll down an incline and then roll up another incline. And when he saw there was bumps and skids and stops and all sorts of stuff, so he said, well, wait a second, it looks like something's trying to happen here, but I also see a lot of roughness in the motion. So he would sand down the surfaces and polish them up real smoothly, and then there'd be less hiccups in the motion. And what he realized is when an object would roll down an incline, it would try to get to the same height on the other side of the incline. And he would polish it again and get closer, and he polished it again and get closer. So finally he reached the conclusion that generally, if you let something roll down an incline, it's going to roll down the incline, and then it's going to roll up another incline, and it's not going to stop until it reaches its initial height. And if that second incline was really, really, really gradual, that thing might go hundreds of miles before it ever got the height. So again, he's reaching the conclusion that an object in motion tends to stay in that state of motion. He even invented a clock because he didn't really have good timepieces, but he invented a water clock where basically you open up a valve at the instant you wanted to start timing something, and then at the instant it's over, you close the valve. He would catch the water and weigh it, and he didn't know how much time there would be. If you had 3 kilograms of water, he didn't necessarily know how much time that meant, but he knew for a fact if that was 3 kilograms of water, then whatever took 6 kilograms of water was twice as long. And if whatever took 9 kilograms of water was 3 times as long. And using that, he was able to make it mathematically sustainable and understandable. He could literally quantitatively study it. Not only that, he was hypothesizing things he couldn't make, the perfection, the reality, and that sort of stuff. He was hypothesizing those. He was letting the arbiter be not his mind like Aristotle would have you do, but specifically he leaned on experiment. Let's see what experiment shows. And he had no respect for just taking at face value whatever Aristotle said just because Aristotle said it. And he certainly didn't take it if he couldn't show it in the lab. Aristotle's philosophy was almost completely backwards to that, in that Aristotle imagined what our universe was a bastardized version of the heavens. So there was no point in doing experiments. It's like he would say, for instance, the idea of a table is perfection. It's this horizontal surface that can hold up things. It can allow you to lay down. It can allow you to sit down. It can allow you to write. You can stack stuff on it. All this sort of stuff. You can do experiments on it, all sorts of good stuff. But the actual table is kind of crappy because, if I come back 300 or 400 years from now, this table will be nothing but cinders and dust. So they definitely saw a distinct difference between their reality, which seemed to be a bastardized version of the heavens, and what the heavens were. And they sort of went on the assumption that the laws of nature would be more of the heavens. So why would they do experiments on the bastardized version of heaven? Galileo was like, no, let's do experiments on on this world and see what this world tells us. And he got in quite a bit of trouble for that. He had a friend who was a noble person, and she had written him a letter and mentioned something like Joshua 13:10. I might be misremembering that scripture, but she said, well, surely, Mr. Galileo, you can't be taking this seriously, that the sun's at the center, because in Joshua 13:10, God commanded the sun to stand still. And he said, oh, no, dear, no, this is one of the areas where you can't read the Bible literally. You have to read it sort of metaphorically. In fact, if you actually did what the Lord supposedly did in that passage, you would have actually had the opposite effect. Instead of the day lasting for a really long time, the day would have disappeared really quickly. You can imagine a Catholic Church that had just dealt with Martin Luther and Giordano Bruno would probably not be cool with Galileo interpreting scripture for them. So that was a bit of a problem. But Galileo did get that law of inertia. And basically what Galileo found was that an object tends to maintain whatever motion it's exhibiting, unless there's a force acting on it. And he would say it's as if it has some inertia. And that inertia is not really an answer. I mean, it's a name for what is going on, but it's more or less just a name to make you feel a little bit better about dissing Aristotle, if you will. But it really doesn't answer the question any more than dark matter answers the question about where's the missing mass of our galaxies, and dark energy answering the question of where's the universe getting the energy to speed up. But those are both names that we've given it so we can refer to it, but it doesn't answer the question. So Galileo, didn't necessarily know the answer. He just knew the laws of the universe seem to be suggesting that an object in motion tends to stay in that state of motion. And the only thing that makes it not move at a constant speed in the same direction is a force compelling it to slow down or speed up or change directions. So that became Galileo's law of inertia. And later Newton would go on to write his version, which it says an object in motion tends to stay in that state of motion unless acted upon by a net external force. If you want to use the word vector word with that, it makes it even more succinct. You can just say an object will have a constant velocity vector unless acted upon by a net external force. Because by saying a velocity vector, you're specifying even if the speed is 0, even if the direction is 5 degrees east of north, all of that stuff's going to stay the same unless there is a net force acting on it. So that's Galileo's law of inertia, which turned into this latest version being Newton's first law of motion. Newton's second law of motion was one that's more or less of his own doing. It's not something that he borrowed from anyone else or that someone else had necessarily figured out. But let me show you what it is. So I'm going to do share screen. And now I'm going to tell my iPad to share the screen. Okay. So this should come up any minute now. So you can get these wordings from your book. You should definitely, anytime you have a book that's a chapter named after a particular law or a particular set of laws, your reflexive instinct should say, oh, maybe I should commit these to memory. And I would agree with you 100%. You should not only know Newton's laws of motion, you should know exactly which one's the first law, which one's the second law, which one's the third one. So the first one really is Galileo's law of inertia, which was sort of reversed into Newton's first law of motion. The second one, I'm going to use vectors in, even though Newton had no idea about vectors. I'm just going to use it because it makes some points that are a little more helpful. But what Newton discovered was that an object will achieve an acceleration A, and that acceleration is directly proportional to the net force acting on the system. Now, this is something I do. I wrote that sigma next to the F. That sigma is the same sigma from the Greek alphabet that gives us the word summa. So, for instance, you probably have heard that you can graduate summa cum laude or magna cum laude or cum laude. Laude means praise. Magna means great or big, and summa means sort of the sum of all praises. So the summa cum laude is supposed to be the greatest. So we use that phrase summa and that symbol sigma specifically to remind us that, hey, if you want to calculate the acceleration of an object, you can't take a particular force and say that A and F are thumbs up, which they are, but you have to say A and the net force, the total force acting on the system, are thumbs up, thumbs up. Thumbs up, by the way, can be interpreted whenever you have the two variables on opposite sides of the equals, like A's on one side of the equals and the total force is on the other side of the equal, but they're on the same side of the fraction bar. And you might look at this and say, well, there's no fraction there, but you got to remember that you can write any number over one and then it becomes a fraction. So now you see that, in fact, the A and the sum of all the forces are actually both in the numerator on opposite sides of the equals, and that means they're thumbs up, thumbs up. Now, they're also, the exponents are one, so it really means like a one-to-one correspondence. If I double the total force, then I double the acceleration. If I triple the net force, I triple the acceleration. Or if I increase the net force by a factor of 1.782, then I increase the acceleration by a factor of 1.782. So that's what that kind of motion means. But there's also another variable that matters. And what we find with that variable is that the acceleration is inversely related to the mass. Okay. So that's what we call thumbs up, thumbs down, like this. And thumbs up, thumbs down basically is the case when they're on opposite sides of the equal sign, but also opposite sides of the fraction bar. So as you can see here, the M is on the bottom and the A is on the top, even though they're on opposite sides of the equal. So they're thumbs up, thumbs down. And what that means is if you double the mass with the same force acting on it, then the acceleration is going to go down by a factor of 2. If you cut the mass in half, the acceleration is going to go up by a factor of 2. So this is a version of Newton's second law. I normally write it not like this, even though that's kind of a useful way. I normally write it like this, where I'd say the summation of the forces is equal to mass times acceleration. And of course, we'd also want you to recall that we learned before, A is dv dt, which, using the nomenclature that we had in chapter 3, you could also call this d2r over dt squared. It's the second derivative of the position vector with respect to time. So you can see already, if that's really Newton's second law, we have a second order differential equation that's sort of going to be the hallmark of physics, at least for the Newtonian, what we call classical physics. Any questions on that? So this one's Newton's second law.
How many laws is it in total?
Depending on how you call it, it's 3 or 4. So we have Newton's 3 laws of motion. There's Newton's first law: an object in motion tends to stay in that state of motion unless acted upon by a net external force. Then we have Newton's second law that says the net force is equal to mass times acceleration. And notice the vector part of it allows me to let everybody realize that the acceleration will be parallel to the net force. And then there's Newton's third law: for every action. Y'all can fill in that part.
There's a reaction.
Yep, an equal but opposite reaction. That's Newton's third law. And the reason why I said it depends on how you clarify it or how you say it. There's also Newton's universal law of gravitation, which could be sort of considered a fourth law, but no one ever calls it Newton's fourth law of motion. It's just Newton's law of gravity. So all 4 of those are ones you should know. So we've gotten the first law, we've gotten the second law. Now is time for the third law. And the third law basically says, for every action, there's an equal but opposite reaction, which I like to write like this. If an object B applies a force to object A, that force should be called FAB. And that force is equal in magnitude but opposite in direction to FBA. So what we're saying is the force on object A due to object B is equal in magnitude but opposite in direction to the force on object B due to object A. Okay, so literally for every action, FAB, there's an equal but opposite reaction, negative FBA. So if it doesn't matter, by the way, whether, quote unquote, your force wins. Like if you know this piece of drywall in your house you're getting ready to punch, if you look at that piece of drywall between 2 2x4s, that you happen to know where they are so you don't accidentally punch a 2x4, you might reach a conclusion that that drywall will break with a force as small as maybe 150 newtons or 150 pounds. By the way, Newton is a unit of force that we use, and I'll define that in a second. So if it really takes 150 newtons or 150 pounds or 150 tons of force to break something, when you break it, that doesn't mean that that force isn't applied to you. According to Newton's third law, if that's the force that is required, then you put that force on the wall to make it break. And that wall, independent of whether it breaks or not, is going to put that force right back on you. So you'll probably know of at least one person in high school that broke his hand or some fingers or something, doing something stupid, punching something. And that's largely the calculation that you do. You can break stuff, but that's not a free ride, because whatever force you have to apply to something, that same force is going to be applied back to you. In the one of the typical books that you use for a conceptual physics class, like some people call the course physics for artists or physics for dance majors or stuff like that. They often will word this as you can't touch without being touched. And that's a decent statement. Even if you just talk about touching someone on their cheek, whatever force you apply to their cheek is going to apply to you. Now, it gets a little bit neater than that, in that you can make certain conclusions that at least superficially sound really, really good. So, for instance, if you've ever tried to punch a piece of, let's say, a square of toilet paper that's falling, right? If you try to do that, or if you try to kill a housefly that's flying loose in the air as opposed to being set on a table or a wall or something, and you're hitting it with a fly swatter, you'll notice that little sucker is going to live most of the time. And one way you can think about it, and this is a highly superficial way, but it sort of is right. The reason you can't apply a great deal of force to a fruit fly or to a piece of tissue paper is that Newton's third law says that whatever force you apply to a fruit fly or a house fly or tissue paper, that fruit fly or house fly or tissue paper has to be able to apply that same force to you. So if you wanted to put 1,000-pound force on a fruit fly, good luck with that, because I can't imagine a way in which a fruit fly can put 1,000-pound force on me. So that's sort of the quick and dirty way of explaining why we can't, or why we have such a hard time killing a fly in the air as opposed to one that's sitting on a wall or sitting on a table or something. If you want to think about the details of it a little bit more so that you hopefully thoroughly understand it, you really need to think a little further. So you can imagine, for instance, Novak Djokovic, the guy that won the U.S. Open this weekend, and I think it's Flushing Meadows, New York. He has about 150 mile per hour serve. And when he's doing that, you can imagine the hand is extended. He's pretty tall anyways, but his hand's extended and then the racket's extended beyond that. And in order for the ball to actually go 146 miles per hour, the strings more or less have to be going 146 miles per hour when they let go of the ball or when the ball falls off of them going towards the other person. So you might think, at least from a reasonable standpoint, that probably his hand's going at least 100 miles per hour. And that's consistent with, professional baseball pitchers. When they throw a ball, if they actually throw a ball at 100 miles per hour, their hand has to be moving at 100 miles per hour when it releases the ball. So we can think of Novak, or we can think of one of the professional pitchers as if their hand's moving at 100 miles per hour. Now, let's imagine them using that to try to kill, say, a fly. Well, a fly maybe weighs, I don't know, 10, 15, 20 grams, something like that, a very small amount of weight. And of course, the unit of force, or excuse me, the unit of mass that we use in Newton's second law is the kilogram, not the gram. So, 20 gram fly has a mass of 0.020 kilograms. So if you want to take F equals ma and say, okay, well, how much force does it take for me to hit that fly? Well, what happens is when you swing, you being Djokovic or whatever, when you swing at 100 miles per hour, what's going to happen is your hand is going to hit that fly. The fly's body is going to cushion a little bit, and then your hand's going to cushion a little bit. And probably that's about all the absorption of the force you get is your hand squishing in maybe 2 millimeters, and maybe the fly's body squishing in a millimeter or so. But in that small time period, the fly is going to go from essentially 0 miles per hour to 100 miles per hour. And that might take on the order of a thousandth of a second. So 0.001 second, something like that. So the acceleration would be like 100 miles per hour divided by, 100 miles per hour minus 0 miles per hour divided by 0.001. You can see that acceleration is pretty large, but guess what? You're now going to multiply that acceleration times m, as Newton's second law of motion shows you, and that m is 0.02. So you've already cut down the force by a factor of 2, and next thing you know, you have a force that's actually quite small. So yes, it's correct to say that. That you can't apply a big force to a fruit fly because a fruit fly can't apply a big force to you. You can now sort of work out the dynamics of why that's the case. For instance, if I took 100 miles per hour and converted that to meters per second, we'd say 100 miles per hour. So I'm going to convert that miles to feet. I'm going to say divided by 5280. That's feet per hour. Now I'm well, actually, I'll do this some other time. But anyways, we could actually figure out 100 miles per hour. I usually have a HP calculator that just does that really quickly for me. But I also have access to other stuff. So I'm going to use some of that quote unquote other stuff. So I'm going to say 100 mph to meters per second. 44.7. So if you look here, we say the acceleration of the fly is equal to 44.7 meters per second minus 0 meters per second. And now what's the time? Well, the time's really the time required for the fly to go, let's say, essentially 4 millimeters at 100 miles per hour. So velocity equals distance divided by time means time is equal to distance divided by velocity. So if I take 0.005 4 meters and I divide it by 44.7 meters per second, we can get that 0.004 divided by 44.7 gives me 8.9 times 10 to the negative fifth seconds. So we can now say this is going to be divided by 8.9 times 10 to the negative fifth seconds. And I'm going to say 44.7 divided by that answer that I just calculated. And that gives me that gives me basically 5 times 10 to the fifth. And that's meters per second every second. So that's the acceleration it gets. Now I'm going to Google real quick mass of a housefly. So actually, my thumb wanted to write a horse with an hours fly. Whoa. Okay, it gave it to me in ounces, in grams is what I would like. Oh, that's a lot smaller than I expected. So they're saying the mass of a fly is 0.048 grams. That actually helps a little bit. So now I can say the total force is equal to the mass, which is 0.048 grams times 1,000 grams is equal to 1 kilogram times the acceleration, which is 5.00 times 10 to the fifth meters per second every second. So I can now say that 5 times 10 to the fifth times 0.048 e to the negative 3 gives me about 23.9 newtons. So even with that extreme, literally letting the fly speed up from 0 to 100 miles per hour in 4 millimeters, okay, even that extreme of acceleration, which is probably a little bit of an overkill, we still only get 23.9 newtons of force. And a newton, by the way, is about a quarter pound. So if you divided that 24 by 4, you're going to get about 6 pounds is all the force you can muster on that housefly. So that Newton's third law, that is a full-throated explanation of why Newton's third law says you can't really hit a fruit fly or mouse or housefly very hard. Anybody have any questions on that? Okay, so the 3 laws are Newton's first law of motion. An object in motion tends to stay in that state of motion unless acted upon by a net external force. I'm going to go ahead and explain that net force means you've got to add up all the forces acting on the object. So that's what that sigma was about in the thing I just showed you. So net force. And then I said external force. That means one part of the system can't be applying a force to another part of the system no more than you can literally lift yourself up by your bootstraps. You just can't do it, right? So that's not the kind of force that's included. So an object in motion tends to stay in that state of motion unless acted upon by a net external force. So when you add all those external forces up, all the forces that other things are applying to that mass, not other parts of that same mass, when you add those forces up, if you get something other than 0, then yes, you can change its velocity. And an acceleration is an instantaneous rate of change of velocity, but that can be done by speeding up, by slowing down, or by changing directions. So all of those are fair game. And in fact, that's exactly what Newton was able to use when he came up with his law of gravity. He wrote that he was sitting under in his apple orchard, And ostensibly, the image is that he's sitting under an apple tree and he looks up and sees an apple. And then in the distance behind the apple, he sees the moon. And at that point in time, he realizes how similar they are, which, never mind the fact that that's kind of crazy that you think a moon and an apple are similar. But what he's meaning by that is if he allowed that apple to continue to grow for a few more days, it would get more and more water and it'd become quite succulent and all that good stuff. And eventually it gets so heavy that the stem couldn't hold it anymore and the stem would break. And then that object would fall, that apple would fall in such a way that it's speeding up 9.8 meters per second for every second it falls. Or since it's not going to fall even a whole second, it's going to fall about or change its velocity about 0.98 meters every second for each tenth of a second it falls. So 0.98, 0.98, 0.98, like that. He knew that's the way an apple would behave. And then he's looking at the moon and he realized, wait, the moon would more or less just go straight by the earth if it wasn't for some kind of force acting on it, because some force must be causing it to change its direction, even though its speed is fairly constant. So he was able to calculate that acceleration as well. It's v squared over r. And v is just 2 pi times the radius of the orbit divided by about 29.8 days, something like that, and convert it to meters per second, and you'll get an acceleration. So he said, I wonder if the thing causing the apple to fall is the same thing that causes the moon to fall in some sense towards the center of the earth. Well, what he understood was that the center of the earth was 1 Earth radius away from the apple. Obviously, it's maybe a little bit more, maybe a little bit less, depending on where he was at. But the main thing is it's very insignificantly different from the radius of the earth, because the radius of the earth is so much bigger than the height of any tree. So at that distance of 1 Earth radii, we know the acceleration due to gravity is 9.8 meters per second every second. So if you actually did that and you said, okay, well, this is the acceleration due to gravity at 1 Earth radius, and then he thought, wait a second, I know that the moon is 60 Earth radii from the center of the earth. And he had been studying light and how it behaves. And one of the things that light and sound both do is that their ability to influence their environment falls like 1 over r squared. So if you double the distance away from a light bulb, for instance, you cut the brightness that it gives you down by a factor of 4. If you triple it, you cut it down by a factor of 9, so on and so forth. Well, what happens to an acceleration of 9.8 meters per second at 1 Earth radii? So A at 1 Earth radii, and this is the symbol they use for Earth, equals 9.80 meters per second every second. So what does A at 60 Earth radii mean? I told you if we double the distance, we cut the accelerate, or if we cut the brightness of the light down by a factor of 4. If we triple the distance, we cut it down by a factor of 9. If we quadruple it, we cut it down by a factor of 16. So how much will the acceleration be cut down by going a distance of 60 r? Anybody?
$3,600.
Exactly, 3,600. And if you divide 9.80 by 3,600, you get 0.002722. And that's in meters per second every second. And lo and behold, if you actually calculate A centripetal for the moon, which equals v squared over r, you get 0.002722 meters per second. At that instant, Newton is the only person on planet Earth that knows exactly why the moon orbits the earth and exactly why Mercury, Venus, Earth, and Mars, Jupiter, and Saturn all orbit the sun. He's figured out the law of gravity. He's found out that the law of gravity is F is inversely proportional to the square of the distance away. And later experiments show that it's also proportional to M1 and M2, where M1 would be a object experiencing a force due to M2, and M2 is an object experiencing a force due to M1. So ultimately, what he found was the force of gravity, we'll get into this later, is G M1 M2 over R squared, where R is the distance between M1 and M2. So that's Newton's law of gravity. And that just came about because he understood the first law of Newton, which says that an object in motion tends to stay in that state of motion unless acted upon by a net external force. So if you see an object that's not moving at constant velocity, remember velocity, the thing that has magnitude and direction. So if you see something moving in a non-constant velocity, you know there must be a net force acting on it. And that's what Newton used to reach the conclusion that there was a force acting on the moon. And from that, he was able to determine what that force was. So that's Newton's 3 laws of motion. I want to tell you also that Newton's law of motion, Newton's second law, the summation of the forces, in terms of units, that is going to be called the unit of a Newton. And of course, the summation of the forces is equal to mass times acceleration, tells us that the unit of the mass, of course, is the kilogram, and the unit of the acceleration, of course, is the meter per second, like that. So you can see that the summation of the forces is equal to mass times acceleration, means that 1 Newton is defined to be 1 kilogram meter per second squared, and that's exactly right. And 1 Newton, well, let me write it this way. 1 Newton is on the order of 0.25 pounds. Your book actually has a better figure, but just as a rule of thumb, just think it's about 1/4 pound. So a Newton is a really small unit of force, but still it's one that we use. Anybody have any questions on that? And this pound symbol, of course, hopefully y'all know that that's another symbol for the pound. So, all right, so that's the units that we're using. Now, what I want you to understand is we have the benefit that now that vectors have been created, we can actually write Newton's law of motion without a bunch of sentences. If you look at Newton's Principia, yeah, I have a copy of it here, but that'd be a nightmare to try to pull out. So I'm not going to do that. But Newton's Principia, he mentioned his law of gravity. And basically the way he stated his law of gravity is that there's a force of attraction between any 2 objects that have mass. And that force of attraction is proportional to the product of the masses and inversely proportional to the square of the distance between them. Now that just gives you the magnitude. He also went on further and said, and the force acts along the line that connects the 2 masses from one center of mass to the other center of mass. So that gives you the actual direction as well. And the fact that they're always attractive forces, there's never repulsive gravity, then you know exactly which direction the gravitational force acts. So we're lucky we have vectors, so I can just say F equals MA and put a vector symbol over the F and the A. And since M can't be negative, we can tell immediately that the acceleration has to be exactly parallel to the total force. Okay. Any questions on that? All right. So one thing I want to do is I want to go ahead and show you this. Let's imagine an object in free fall. Now, remember, free fall means it's falling, and we're specifically talking about the earth, on the earth or near the earth's surface, but it's falling and the air resistance is negligible. Okay. So if we were to draw such an object, it might look like this, and it would have a mass M, and we could make our coordinate systems any way we want to. I'm going to actually assume that this is the positive y direction, say. and that's the negative y direction. Now, there is a quantity that's associated with the force of attraction between the Earth and an object, and it starts with the letter W. Does anybody know the name of that thing that I'm talking about?
Weight.
Exactly, weight. So what we know is in free fall, this object has a force called W acting on it. And in fact, that's the only force. This thing right here, this figure I've drawn is called a free body diagram. Okay. And we're supposed to take Newton's laws of motion, which says the summation of the forces is equal to mass times acceleration. And since that's a vector equation, that gives us the summation of the forces in the x direction is equal to mass times acceleration in the x direction. It gives us the summation of the forces in the y direction is equal to mass times acceleration in the y direction. And it gives us that the summation of forces in the z direction is equal to mass times acceleration in the z direction. Okay. Now, when you're dealing with vectors, their magnitudes are always positive. There's no such thing as a negative magnitude for vectors. But there is such thing as a negative component. So when we're writing these equations with the subscripts x and y, they actually do have positive and negative components. So it's okay to do that, but that's not the magnitude. Magnitudes are always positive. So if we look at this summation of forces in the y direction equals mass times acceleration in the y direction, what are all the forces acting on this body of mass m? From this, the free body diagram is supposed to show all the forces. So anybody want to give me all the forces acting on that body of mass m that I drew?
Gravity.
It's the W. I think that's what I heard you say. And notice that's pointing in the positive direction. So I'm just going to write W. Now, we know its mass is m, but here's the kicker. Do you know what acceleration it has since it's in free fall?
V.
Gravity.
Yeah, exactly. So A, since it's free fall, implies A is equal to G. And downwards, the positive directions, according to my axis. So I'll just say W is equal to mg. And now we have a new equation. This is how you calculate weight. So for instance, a 1.00 kilogram object has, whoa, Nelly, has a weight of 9.80 newtons. Because if you take 1 kilogram and multiply it by 9.8 meters per second, you get 9.80 newtons. Does that make sense to everyone? Anybody have any questions on that? All right. So now that we know that, I want to tell you that us here in America, we're the greatest superpower in the world, and we only us and one other nation is this awesome. There's only 2 nations in the entire planet and I should say on the entire planet, that uses the imperial/British system of weights and measures. And America is that one country. Anybody know what the other country is?
Yeah.
You would think it's like Great Britain or something like that. It's actually Liberia. So poor little Liberia, they're the only country that's still using it. At least last I checked, though, they were, but they're the only ones using it. But there's a weirdness going on with the British system versus the SI system. So I'll write this down so we can understand each other. British/imperial system. And then the SI which is also called metric system or whatever. And let's say we have a unit of mass. Actually, I don't want to put it up that high. I'll put it right here. So mass. In the metric system or the SI system, the unit of mass is the kilogram. That's the fundamental base unit, even though it does have a prefix on it. It's just the gram is so small, we don't need it. Now, here's the odd part. Probably most of you will not know this. Does anybody know what the unit of mass is in the British imperial system? It's quite a winner. It's called the slug. I make jokes about it. It's like, yeah, my wife would really like me, expressing her weight in slugs. She'd really appreciate that. Which, she's not heavy or anything. It's just funny to say that. So, and plus she's over there. So, all right. So here's the weird part. Now, if you go here in America and someone asks your weight, in America we say the right thing. Actually, let me use a different color. In America, we actually give the correct answer. Specifically, the unit of weight in the British system is the pound. Okay. Also pound, also that. However, in the metric system, the unit of weight is the Newton. Okay. Whereas if you literally go to Great Britain and someone asks you your weight, they're going to expect you to answer in kilograms. They might actually expect stones too. I've heard that used still on occasion because some people just know stuff about stuff. But anyways, yeah, the unit of weight is the Newton in the in the SI system, and the unit of mass is the kilogram in the SI system. But someone will ask you your weight in Great Britain and they expect you to give them kilograms. Here in America, someone asks you your weight, they expect you to give pounds, which is actually accurate. So at least in that sense, it's right. I say America's lost all credibility as long as our engineers are using things like this. Has anybody ever seen that quantity before?
Every day at work.
And so you know what it is, don't you, John? It's a kilopound. So it's like, hey, let's steal the good stuff from the SI system and let's just stick to our old crappy system of the British. Okay. But yeah, that's what they do. They use MIPS as well. When I did structural engineering, we used MIPS and KIPS, and this is megapounds. So yeah, that's one of the number one reasons I think we're not doing so well if we still haven't converted. Of course, the European Union was heading us that way, but then the European Union started to fall apart, so we're not pushed by that anymore. So we'll be here a little while longer using the SI system. Anybody have any questions about this stuff? Well, I want to get you started on one particular problem just to show you how it works and to make sure you're aligned up with my face-to-face class. So what I'm going to do, and it doesn't have to be done this way, I just like doing it this way. When you're dealing with Newton's second law, it is a vector equation, and vector equations are fine. The thing is that they're hard to work with unless you happen to have a coordinate system chosen and stuff like that. It's sort of correct to say that, but it's also sort of not correct. You can work with a vector equation and just carry it around and, add one thing to one side, and whatever you do one side, you do the other, and that sort of stuff. But a lot of times you need to actually define a coordinate system and then find components relative to that coordinate system to make sense of what the actual vector equations are telling you. And in order to do that, you obviously have to define a coordinate system. So I'm going to define a coordinate system. And in that coordinate system, we're going to have some nice southern yellow pine wood. And we're going to say that this particular piece of wood has a mass equal to 3.75 kilograms. Okay. And I am going to tell you that there is a force acting on this, and that force is perfectly horizontal, and the force is F is equal to 10.35 newtons. And there's also a retarding force, which we might refer to as like a friction force, but we haven't covered friction yet. There's a retarding force, F, that's going to be 2.70 newtons. What I would like to know is what is the acceleration of this block? So this is like supposedly the world's simplest Newton's second law problem. So what we know is, at least for a certain coordinate, I can go ahead and I'll actually redraw it. I'm going to treat this object as if it's a point object, because that's a lot of times what we have to do. So a lot of times we will take something that's actually a physical body and just replace it. I'm going to replace it, for instance, with a little dot right here, and that's the mass M. Okay, so there's your mass M. And now the forces acting on it that I've shown you so far are this force and this force. And that's pretty much all I've shown you. So I'm going to leave it for right now, but I'm going to tell you something about it in a second. So this is, of course, the same coordinate systems we were using before. So that means this is our x-axis. I don't know why it refuses to put it back on black like I asked. But this is our x force, and that's our y-axis. Okay, so the summation of the forces in the x direction equals mass times acceleration in the x direction. That's going to give us the following. The forces. Now, here's where I'm actually working with components of forces, not the magnitudes of the forces. Okay, the blue force is pointing to the right, and I drew it blue so that we realize it's in the positive direction. So I'm going to write 10.35 newtons. And notice the sigma, I told you, means sum up all of the. So I'm adding them, okay? Well, this red force is pointing to the left, so that's a negative 2.70 newtons. I'm taking the time to write the plus and the minus here because I want you to understand you never subtract forces on the left-hand side of Newton's second law. You're always adding them, but sometimes the components are negative, okay? So that's the left-hand side. The right-hand side is 3.75 kilograms times a sub x, which that's the only acceleration, so I'll just call it a. So if I take 10.35 and I subtract from it 2.70, in other words, I'm adding negative 2.70, I get 7.65 newtons is equal to 3.75 kilograms times A. So I can now see that A is 7.65 newtons divided by 3.75 kilograms. And this gives me 2.04. Notice, remember, I told you the Newton, 1 Newton is defined to be 1 kilogram times meter per second squared. So if I divide that Newton by a kilogram, all I'm left with is meters per second per second. So that is the actual acceleration of this block, 2.04 meters per second. And don't forget, we still are required to know our kinematics. So I could go from that question and say, okay, given that this is the acceleration, how far will it travel in 3 seconds, starting from rest? How fast will it be going after 3 seconds? How fast will it be going after 5 seconds? All those questions are fair game. Just because we got out of the kinematics doesn't mean we're allowed to forget it. So anybody have any questions on that? All right, well, we only got about 4 seconds left. So I want to tell you, when you're drawing these free body diagrams, the rule is this. Basically, anything touching your object should probably have a force associated with it. So, for instance, that green block was laying on the surface of a table. So there should be a force associated with that. In fact, that force is one that I'm going to frequently label F sub n, which means a normal force. And normal means it's perpendicular to a surface. Oops. So it's perpendicular to the surface. So that's the normal force. Okay. And you know that's got to be there, because if it wasn't, we know that the object of mass M has a weight, and something must be counteracting that. So the rule of thumb is everything touching the object will have a force associated with it, but there's also at least one other type of force, and that's the force of gravity, where the Earth is physically not touching this block of mass. So you might think, well, I don't have to put the weight on there, but no, you do, because force of gravity is one of those things that acts at a distance. Other things that act at a distance are the magnetic force and the electric force and the strong nuclear force and the weak nuclear force. So you've got those four forces basically. Well, you got gravity, electric force, magnetic force, strong nuclear force, and weak nuclear force. Those are actually actions at a distance. So you've got to rule those out in addition to everything touching it. But other than that, it's just that and stuff touching it. So the full free body diagram for this is weight equals mg pointing down, normal force pointing up. And I can, from that, say the summation of forces in the y direction equals mass times acceleration in the y direction. In this case, we're imagining someone pulling horizontally on that block of wood while the friction force is pulling horizontally backwards on that block of wood. So the object's not going to be bouncing up and down. In fact, it's not going to have any vertical motion. And because of that, the acceleration in the y direction is 0. So from this, we get the normal force plus the negative of the weight is equal to 0. So we find that the normal force is in fact equal to the weight. So that's something we'll use as well. Next time we'll be doing some inclined planes, the Atwood machine, and some fuzzy dice. So that's it for now. It's actually 6:39, so you guys are free to go. I'll wait for the last person to leave. Have a good one, and thanks for coming. Don't forget, you got a test on Monday.
Hey, Professor.
Yes.
I had a question. So, I'm the person that drives 2 hours of Tidewater,
Oh,
and I
good.
was actually wondering, like, it doesn't matter, like, I know it's a face-to-face test, but I was just wondering if I would be able to take that at home and could just, like, get on a Zoom or, like, just, it's fine if not, because I understand it's a face-to-face test, but I just figured I'd ask because to save the
Yeah,
gas and the
we might be
tolls.
able to do something like that, but I'd have to have you. Do you have a camera? I mean, a phone? Excuse me, a computer that has a camera and can run respond to this lockdown browser and lockdown
Yeah.
monitor?
Yeah, I've done that before, yeah.
Okay, I might be able to do that. Let me look into it quickly. Since you have that long of a drive, I would try to say, well, maybe don't come on that day since it's an open lab day. Yeah, give me a little bit of time. I'll think about that. If you don't hear from me by Wednesday, ask me again. Okay. But that's probably
Okay,
something
thank
to do.
you.
Your test is supposed to be a week from today, so we got a little bit of time. But yeah, I think I can probably do that.
Yeah. Okay, I appreciate it. Thank you.
All right, you're welcome. Thanks, Logan. Anybody else?
Well, I just want to know what I wasn't here last Zoom. I just want to know what was talked about.
The notes are up on Google Docs, but we finished up chapter 3, which was basically the projectile motion stuff. So I gave them some formulas that were not specifically numbered in your textbook, but I told them they were allowed to have them on their equation sheet. So that's probably the most important thing.
What do you mean equation sheet?
For your test, you're allowed an equation sheet. And what I've told students is if you look at your textbook, let me stop sharing the screen here. I'll show you what I mean. If you look in your textbook, your textbook has very specific equations that have numbers next to them. And all of those equations that have numbers next to them are allowed. So let me share my screen again real quick. I'm going to say this is it. Share that. So I'm looking at right here, nothing on that page. Let's look at the next page or the next page. Okay, still the next page. Let's find the one chapter that has no equations in it. That's what I'll do. Okay. So you can see right here, this equation doesn't have anything near it. So that's one you're not allowed to have on your equation sheet. But this right here has 4-1a. So in principle, that means this equation can be written down on your equation sheet, and you're allowed to bring that equation sheet with you to your face-to-face test. And it'll have that equation on it. And you're not allowed to write names of equations or anything like that, but you can say F is the force and it's measured in newtons, or you can say A is the acceleration and it's measured in meters per second every second. You just can't say stuff like that's Newton's second law, because that might be one of the questions I want to ask you. Does that make sense, Richard?
My bad, I was muted.
Oh,
Are we allowed to bring our own, or are you going to provide it to us?
the original intent was me to make one, but that's going a lot slower than I would like. So yes, you should have one. And what I would do is I just start with chapter 1, look for every time they have an equation that has a parenthesis, chapter number, dash, another number by it, go ahead and write it down. As you're doing your homework, you'll probably figure out there's a lot of them that you don't need, and you're free to leave them off, but you're also free to have them on. I don't have a limit to the number of pages you can have. I just have a limit to what equations you can use. So your instructor will look at it and make sure it doesn't have anything untoward on it, but you're free to have that.
All right. Okay. Thank you.
Okay. You're welcome.
Have a nice day. All right.
You too. Thank you. Michael, Gabriel. Oh, Gabrielle, sorry. Alyssa, anybody? All right. Well, I am going to call it a day. It doesn't look like anybody's sending me. It doesn't look like anybody sent me a message or anything. So I suppose Michael.
Did you tell us if we when our next tests are coming up?
Yes, you have. I was telling people at the beginning, you have a test a week from today.
Yeah. Okay. I missed the first couple minutes, so I wanted to make sure.
Yeah. So in lab next time, you're going to meet your lab professor and you're going to have a face-to-face test in there. That should be covering chapters 1 through 4. And it's not like an online test. So you're not allowed to do Google searches. You're only allowed to have an equation sheet and a scientific calculator. You can't use your computer, or you can't use your phone for your scientific calculator. But like I said, you are allowed an equation sheet.
Okay, and is that going to be done online, or do we have to go to a?
You actually have to go to the lab, and the lab instructor will watch you. The way it works, it depends on how many computers there are at your lab. But if you're a person that has a laptop that you don't mind bringing with you, and the laptop works on TCC Wi-Fi and can run Respondus and all that stuff on TCC's internet and Canvas, then yeah, it would be nice if you brought it. And all you have to do is turn on your lockdown browser, and the instructor can monitor you that way. But you do have to have it on lockdown browser, or it won't let you take it.
Okay.
Because I usually do it on the computer, and that way you get your grade immediately. But there occasionally might be 1 or 2 questions where I'll ask you to turn in your work for it, or where it'll be an open question so that it's not a multiple choice. You have to type in an answer or something, and you turn in your work for that. But generally, they're almost always all multiple choice.
Okay. Okay. Thank you.
You're welcome.
You have a great day, Professor.
You too, Alyssa. Gabrielle, Michael, anybody? I think they might not be here. All right. Have a good one, everybody. Bye-bye.